Okay, thank you very much, all of you, once again for joining. And today is actually, we did some calculations yesterday, and we were thinking about fields expanded in the black hole spacetime. Today we'll reap the fruits of what we sowed yesterday, and actually in the past 3 lectures. And we are going to, I hope, at the end of this lecture, have a very nice formula for Hawking radiation and a nice derivation of Hawking radiation that we should be able to conclude today, both in flat space and in anti-de Sitter space. So before I go there, I just wanted to explain a little bit what we did yesterday. I just wanted to recap very quickly what we did yesterday. What we did yesterday was we said, we took some field which satisfied some Klein-Gordon equation in a black hole spacetime, and we expanded it, and we said that outside the horizon, this field has some behavior which looks like this. R star into some YL omega plus some B omega L into some function that we called F in R star into again YL omega into e to the minus I omega t plus the Hermitian conjugate part. And in principle, one can, of course, find these functions f out and f in by solving the wave equation. But what we said was that these functions f out and f in have some very simple behavior if you look at how they behave near the black hole horizon. And we said, look, near the black hole horizon, as r goes to RH, and let me write RH plus, we find that this function f out just looks like e to the minus I omega r star plus some factor which we call g omega L into e to the I omega r star. Okay. And we said that, there was some, this function f in had some other behavior, which we said was h omega L into e to the, sorry, I hope I got the factors right. Sorry, I messed up my minus signs. 1 second, please. Should put a minus sign here, and this looked like. Okay. This was the behavior of these modes, and these modes d omega L and h omega L, which, as I described many times yesterday, came from demanding that these two modes should be orthogonal in the Klein-Gordon norm, actually have a lot of physics associated with them, which we will explore in the forthcoming assignment. These d omega Ls, in fact, are very closely related to what are called the gray body factors of the black hole. And there's a very simple relation one can derive between these d omega Ls and the gray body factors of the black hole. But for us, that's not so important. We just wanted this specified behavior near the horizon. Then we said, if you looked at the behavior inside the horizon, then you would find something else. Then you would find that the behavior inside the horizon looked like something which was a tilde omega L. Okay. And this a tilde omega L now multiplied e to the I omega t with a factor of YL star omega. And then there was another oscillator, which we call C omega L, which multiplied e to the minus I omega t into YL omega. And this whole thing multiplied some function that we called F tilde, which was a function of R star. Once again, you could have found this function F tilde out just by solving the wave equation. But all we did was we just demanded that this F tilde out had some specified behavior now as you approach the horizon from inside, and that behavior was just that it went like e to the minus I omega R star. By the way, I should say that in the review, even though in general I've been emphasizing that the notes are less accurate than the review, I noticed while I was preparing these notes, there's actually a typographical error. This AL tilde does not multiply a YL star, it's multiplying a YL, whereas there should be a YL star in the review. So if you happen to look at the review, please just make this correction in your mind while you're doing it. Okay, so this was the summary of what we said yesterday. And one last thing we said was, these modes C omega L were related by continuity to these modes A omega L and B omega L. But these A tilde omega L modes were just new modes. Okay. So now we have in front of us on the slide a summary of everything. I mean, the summary of the important results that we derived yesterday. Okay? So now we are going to see how these very simple results and the field expansion just outside the horizon. So this is the field expansion. This controls the field expansion just outside the horizon. And how the field expansion just inside the horizon is sufficient for us to be able to derive the form of Hawking radiation. Okay, so that's going to be what we're going to achieve today. Okay, good. So how do we do
I
that?
have a little question here. I'm sorry.
Yeah.
Why is the sign of omega alternating in the inside solution, but not in the outside solution?
Why is the sign of omega alternating? Remember, so maybe I forgot to write an HC. So there should be a plus HC here. There is always an e to the I omega r star term and e to the minus I omega r star term in both solutions. In the expression on top, the e to the minus I omega t was what we used to identify annihilation operators. And then there's a Hermitian conjugate which has an e to the I omega t and has an e to the I omega t plus r star and an e to the I omega t minus r star. In the expression below inside, I've clubbed the annihilation operator. The annihilation operators are the things that multiply e to the minus I omega r star because r star is playing the role of time. But the two different kinds of degrees of freedom we have, the left movers and the right movers, if you like, are multiplying e to the I omega t and e to the minus I omega t. Right? So you see that in both expansions, you have an e to the I omega t plus r star, e to the I omega t minus r star, and e to the minus I omega t plus and minus r star. So you have all four terms appearing on both sides. But it's a question of what we call the annihilation operators. And I've called A tilde and C are the annihilation operators. And then there are the Hermitian conjugates which are here. Okay. And so it's a question of how we've written the terms, what we call annihilation, what we call creation. Okay, good. So now let's look at how now we can just put together everything that we've been talking about in the past few lectures and obtain a form for Hawking radiation. So we already mentioned in the previous lecture that if you looked at the metric near the horizon, okay, in these so-called crucial coordinates, it looked like this. Okay? And then there are, of course, deviations away from this form, which are these dots, which depend on what happens when you go away from the horizon. Okay? Now, this should already remind you of something that we saw in the first two lectures, where we discussed extensively how one could define near horizon modes when the metric has this form. Okay? So what we're going to do now is we are going to define these near horizon modes. So remember, we've been talking about the field, and the field has some behavior and some expansion. But now we can define some near horizon modes, and that's because near this horizon, the metric has the form that we require to define these near horizon modes. These near horizon modes in some geometries with spherical symmetry. And I'll just remind you of what the formula for defining those near horizon modes was. And the formula, let me remind you, was this. Okay. We had some formula which you will find in your older notes, but which look like this. Okay. So there was a du phi, there was some u, v equal to 0, omega, a minus u to the minus I omega naught, some smearing function, and some yl star omega, and some du and d omega. Okay. So this was what we called a near horizon mode. It was just some integral of the field, right? So if you're given a field, you can just, you're given some field, some scalar field, you can just do this integral, this extracts some operator, this defines some operator. And this is what we call the near horizon mode. I'm sorry, my handwriting is so bad, but I'm trying to write NH here, which may sometimes look like HH or NN, but I actually mean to write NH, and my N's and H is kind of look the same. So let me try harder. Okay. I always thought once you graduated from high school, you'd never had to worry about handwriting. But unfortunately, I find whenever I write now on a blackboard, it's confusing. But nobody can penalize me, at least for it. But please don't get confused by my bad handwriting. Okay, so we had also these near horizon modes. Remember we always defined a pair of near horizon modes. We define these modes A's and we define these modes A tildes, and these modes A tildes look like this. I'm just writing down a formula that you have already seen. And remember, we had the smearing function and we had various things. And remember, note the opposite signs of the spherical harmonics. Okay. Now, we have already an expansion for the field, right? We spent so much time in the last lecture trying to write down some expansion for the field. Therefore, in principle, you could give me some specific smearing function, or I could choose some smearing function, and I could take that expansion for the field and I could plug it in, and I could work out carefully what these modes A NH and A tilde NH are in terms of the operators A omega, B omega, A tilde omega, C omega, and so on, right? There's absolutely no difficulty in doing this integral carefully. Okay, so we can do this integral explicitly. Okay, but in fact we don't have to do the integral. One could do the integral, and it's if you like, as an exercise, you can go ahead and take the expansion that we wrote down and try and do the integral, and you will get some form for A NH and A tilde NH in terms of the operators that define the field phi, right? Because the field phi has an expansion which just works everywhere, and you can use that and obtain some expression for A NH and A tilde NH. But it turns out that we don't need to do that, and that's for the following reason. The reason is that, remember that near the horizon, what does the field look like, right, for a given frequency? So we said, the field looks like, let me now drop all the constants and so on. It looks like some sum over omegas and L's and so on. I'm being very precise because I just want to argue what the result is. And then there's some e to the minus I omega t, right, into an A omega L. Okay. And then there are these expressions which look like an e to the I omega r star plus a g omega L into e to the minus I omega r star, right, plus terms with b omega L. Okay. But now stare at these terms carefully and remember that the Kruskal coordinates that we defined were also defined by capital U is u to the t minus r star raised to some power and with some other additional constants up there. So that tells you that this expression we have, this first expression we have, can just be written as A omega L into u to the I omega divided by k. Remember, this k is the surface gravity plus some other term which is g omega L into v to the minus I omega by k. Okay. Notice the reason this happens is because u looks like e to the k, okay, into r star minus t. Okay. And that's why you see that, and there are constants up here which I'm not writing down. Okay. So this is everything is up to constants. And the reason I'm not writing down the constants is because the constants are not going to matter in the end. We are going to be able to write down an answer which doesn't involve which doesn't involve these constants, and that's the reason I'm not being careful about them. It's one of those remarkable situations where you can there's a certain set of constants that just has to work out correctly, and you could do various things to work the constants out, but you don't have to keep track of them in individual calculations. You know what the answer is going to be in the end, which I'll explain in a minute. I'll justify my carelessness in a minute. But for now, I just want to point out that this term and this term combine to give you this term, right? And I hope that is clear. Whereas this term and this term combine to give you this term. Okay? And I hope that is clear as well. Okay. So and of course, if you look at the b omega L terms, okay, the b omega L's multiply a different set of terms. They multiply something which looks like e to the minus I omega t into e to the minus I omega r star, okay, also into some yl omega, but we don't care about that. Okay. And this looks like b omega L into v to the minus I omega by k. Okay. Again, up to constants. So if you think of the expansion of the field near the horizon, okay, I emphasize near the horizon, you find that the expansion in terms of the u and v coordinates looks very simple. It just looks like u to the I omega by k and plus something which multiplies v to the minus I omega by k. Okay, now look at the expression we are using to define the near horizon modes. Look at this expression that we have to define the near horizon modes. Focus on this expression. Okay? If you focus on this expression, you will see that this expression is multiplying something with a minus u to the minus I omega naught and doing an integral, right? So remember, these integrals that we're doing are effectively like Fourier integrals in log of minus u and log of mod u. And so you see that this kind of integral is going to pick up the u to the I omega naught terms from inside this, right? It's going to pick up the u to the, it's going to pick up the terms which behave like u to the I omega naught inside this. Whereas this kind of integral, the integral here, is going to pick up the terms that behave like u to the minus I omega naught. Okay? So you see that when you do this integral, when you think of the expansion of the fields in terms of the A omega L's and in terms of the B omega L's, there is only one term here which behaves like u to the I omega, and that's this term, right? And therefore, you see that you have a nice, it must be the case that these near horizon modes, whatever they are, right, must look like, these A and H modes must look like some A of, some function, right, omega L, omega prime L into Q of omega prime omega. Okay. Because they're going to pick up the A modes and they're not going to pick up the B modes. So once again, everything we say is true, it's true in the limit that these smearing functions are long and so on, and there are always these dot terms that we are ignoring. But you see that, which we discussed at length. But you see that this A, up to in this approximation, you see that these near horizon modes have to pick up the A omega L terms, and the A omega L terms have to be multiplied with some smearing function. Okay, but what can this smearing function be? This smearing function has to be very sharply concentrated, and that's because we emphasized many times when we were looking at these near horizon modes that these kinds of Fourier integrals led to things that were almost delta functions. So in fact, we will find that A and H looks like A omega naught KL, okay, which means that this integral is going to pick up this Q omega prime omega picks up modes only from A, from near, okay. It only picks up, sorry, I didn't need a, sorry, excuse me, there's, it only picks up modes from near near A omega, sorry, I made a slight mistake in my notation, which I'll just fix in a second. Sorry, I wrote down two indices here, and that's probably because I should have written this first and written A omega not K. Yeah, sorry. I should have written this expression first and then written A omega L first, because I have an omega that appears here. So you could have asked me, or maybe somebody did in the chat, what the omega was doing here. But the main point is that this smearing function, whatever it's doing, is going to pick up modes which are very close to basically A omega not K modes. Okay? So it's going to pick up some simple harmonic degree of freedom, which we can call A omega not K. Remember, these near horizon modes are implicitly defined with some choice of frequency, and that choice of frequency translates into the kinds of frequencies that you pick up from the global modes, but it translates with a factor of the surface gravity. Okay? So it's not that if you define these near horizon modes with a frequency omega naught, you pick up the same frequencies from these global modes, but rather it's that if you define these near horizon modes with this frequency omega naught that we've been using, you pick up the global modes at a different frequency, which is this frequency omega naught multiplied with K. Okay? And that comes because these global modes are multiplying not u to the I omega, but u to the I omega divided by K. And that's the reason you have this multiplicative factor of k that's sitting up. Okay. Now, remember I said that, you didn't have to be careful about the normalization. And the reason for that is that, we only need first that this q omega prime omega is sharply peaked around omega prime equal to omega. And you see that, if you do that, this integral over q omega prime omega will indeed pick up modes from near a omega naught k. Okay? And notice that's because we said a and h is a times omega naught kl. So it's just omega naught k that's going to enter this omega here. And if q omega prime omega is sharply peaked around omega equal to omega naught, around omega prime equal to omega, then you see that this integral will pick up contributions only from a omega naught k and not contributions from frequencies that are very different from a omega naught k. Okay. The second thing, and this is the nice thing about everything that we did with these near horizon modes, is that we already, we don't have to work out this smearing function q in detail. In principle, as I said, you could do these integrals and you could have worked out what the smearing function was. It's a straightforward exercise which you can do by taking these f out and f ins and integrating them with u to the I omega. But you don't need to do that because you know that after smearing, these a near horizon modes are normalized in a nice way. And so you know that these a omega L modes, these modes that I defined here, are canonically normalized. And that's because these a near horizon modes were canonically normalized. And how did, they were canonically normalized, and that canonical normalization just came from the canonical commutation relations of the fields. So in fact, we weren't even very careful about normalizing these capital A omega prime modes. We didn't say what were the factors of omega that entered into their commutation relations. But all of that, we weren't careful about some whole bunch of other constants in deriving this. But the point is that in the end, the final answer that you get by defining these near horizon modes has to be canonically normalized. Okay? So all the constants have to work out so that the final answer you get for these modes works out correctly. Okay. So the summary is that the near horizon modes become slightly smeared, not sharply, become slightly smeared global modes. Okay. And we don't need to work out the final smearing. We only need to work out the fact that the frequency, when we define the near horizon modes with omega naught, these slightly smeared global modes are picking up frequencies with centered on frequencies, a frequency which is omega naught k. Okay, and the only thing we need is this multiplicative factor, is the fact that you define the near horizon modes with the frequency omega naught and you get slightly smeared global modes with the frequency omega naught k. We don't need the rest of the constants because in the end, these slightly smeared modes the slightly smeared global modes are canonically normalized because the near horizon modes are canonically normalized. Okay, are there any questions about this? I see there's some questions in the chat. Maybe I can stop.
Hello?
Yeah.
So I had a doubt. So the reason we can use the field expansion only near horizon is because of the smearing function, right?
Correct, because the smearing function.
Yeah,
please go on. Complete, please. Yeah.
So as in case we didn't have the smearing function, or if the smearing function was more broad in some sense, then we would have to use the field expansion maybe away from the horizon as well.
Exactly. These near horizon modes, we kept calling them near horizon because we introduced a smearing function to make sure they were only picking up degrees of freedom near the surface we were looking at, right? So exactly for this reason, when we call, when we define, so there's an integral we needed to do, as you point out exactly. The integral was written here. It was some integral over phi and it's some integral over du, right? So you could have said, why don't I need the behavior of the field for large U where it could be very complicated and various other things could happen. But you don't, because you have this function which dies off for large U. And so you only pick up the behavior near the horizon. And the behavior near the horizon is very simple. it's what we wrote down here. It's just given by some oscillatory behavior in the U's and the V's, and that is what is sufficient to give you this result, which is the result that we have here. Okay, so this is a nice result. I want to emphasize that it's an important result. Okay, that we define these near horizon modes and they get related to the global modes using the properties of the geometry of the black hole geometry and the behavior of the wave function near the horizon. Okay. In general,
actually, there's a question in the chat, which is asking, are the subleading terms in the near horizon modes? Are there subleading terms in the near horizon mode expansions which depend on the choice of smearing function?
Yeah. There are subleading terms. There are always these subleading terms that depend on some choice of the smearing function, but we'll never bother about them because we'll always, we can, as I said, provided you have a hierarchy of scales between the scale at which you can define these near horizon modes and the curvature scale, which we do usually, it's between some ultraviolet scale and the curvature scale, you can always make these terms extremely small. And so we are never going to care about these small corrections. We don't need to care about these small corrections for what we're doing, for the leading order result that we want.
Hi, Suvrat. Just going back to the near horizon expansion of the field. You go from having a summation over omega and L, and then you lose that summation, but you still have an omega and an L in that expression. Could you just explain that to me?
I didn't lose.
Before this.
One more here?
There, second line.
Oh, you mean maybe I didn't write down the YL omega? Oh, sorry. No, sorry. That was sorry. It wasn't that. No, it wasn't that I lost the sum. I should have written the sum. Thank you.
Okay.
Yeah. I just wanted to focus on the terms that were multiplying A omega L. I've also, so by the way, I wanted to focus on these ULs. There are also these YL omegas, which I haven't written, which I wrote down several times previously, so I haven't been writing them again. But I just wanted to focus on the U and the V part, and so I was focusing on the R star and the T part, and there is the sum omega L. You don't lose them.
Thank you.
Here I wrote down what B omega L multiplies, so I didn't have the sum to start with. But yeah, I should have written the sum. Thank you.
May I ask to repeat what the definition of those small A omega L is? Because I lost that part while I was taking notes.
Yeah. So this small A omega L is defined as, so this. So it's actually this. You can think of it this way. Okay? You can think of this as being the definition of what I'm calling small omega L. Okay? So if you define the near horizon modes with some frequency omega naught, on the right hand side you get A into omega naught K times L. Once you're given this definition, you know how to define the near horizon modes, which are defined with some frequency omega naught, and therefore you can work out what the smearing function Q omega prime L is. Okay? So you can think of this A omega naught or A omega L, small A omega L, as being just whatever you get with the near horizon modes. I'm just reintroducing the factors of omega and L, which we were keeping tacit in the near horizon modes. In the near horizon modes, I said we define them with some frequency omega naught and some frequency L. I'm just trying to reintroduce that notation, and that's why I reintroduced this. Okay. So these are, if you like, these A omega Ls, let me say it more precisely, are the near horizon modes defined with the frequency omega divided by K and the angular momentum L. Okay, so that's the definition.
Thank you.
Yeah.
Could you explain once more the picking up the factor of K?
You see, the factor of K comes as follows. Look at this expansion. This expansion looks like e to the I omega by K, right? So if I ask, what are the terms, but the near horizon modes are defined with some, with some choice of frequency that we always just call omega naught for some reason, right? Just to keep the notation light. If I ask, what is the expression
I'm
here
sorry,
that goes like...
What is this K? Because we didn't see this before. We just had U raised to the I omega.
No. This K has been appearing all throughout. This K has been appearing all throughout. This K is the surface gravity. The reason the surface gravity is because if you remember, if you look at the relation between Q, T and R star, it has this e to the K sitting inside it. Okay. So I emphasized this at the beginning of the lecture yesterday. U is not e to the R star minus T. U is e to the K into R star minus T. And that K factor is important. And that's why, when you do this U to the I, when you look at the expansion of the fields looks like U to the I omega by K. So if you ask, what is the term that goes like U to the I omega naught here? it's the term which has omega is equal to omega naught k. It's that expression.
Right. Right. Okay, then how does omega k become dimensionless? Because later you have
How does
a label
omega
given by.
k become dimensionless? It has become dimensionless. Omega has units of energy and k is opposite units.
Okay. K was derivative of a function, right?
K was f
if
prime
omega
RF,
k,
but
yeah, I mean, if omega k is dimensionless, then how is omega by k? I'm just confused about this. So omega by k.
No, omega k is not there. Omega by, sorry, one second.
Yeah.
Omega by k is dimensionless, not omega k.
Right, but then later on your label becomes omega k. The frequency becomes omega k.
No, it becomes omega naught k. It's not omega k.
Right.
No, this is omega naught k. So omega naught k now has units of energy. Omega naught is just some number which we use to define the near horizon modes. Omega naught k now has physical dimensions of energy.
Yeah, but omega naught was still a frequency, right?
No, omega naught was, the way we defined it was just some number. It was, you could think of it as it was just some number. Yes.
Right.
So, when we define these near horizon modes, yeah, omega naught k has the correct units.
I see. Okay.
Thank you. Yeah. Okay. Are there other questions?
Sorry, I have one more question.
Yeah.
So you're saying that omega naught is just a number, but the 2-point functions of a and a tilde depended on that omega naught, right?
Yeah, they depend on that a omega naught. Yeah, they depend. Remember the 2 pi. It was 1 by 1 minus 2 pi e to the minus 2 pi omega naught.
Right. So it does have some interpretation in terms of, I mean, these modes a and a tilde do have some relation with these omega naughts. So now, my question is that what is this? I mean, what is this distinction between omega naught and omega naught k? Right?
Omega naught k, omega is now really a physical frequency that's measured with respect to this time that we're talking about, right?
So now if we calculate the 2-point function of these modes, these near horizon modes.
Yeah, so that's what we'll do next. So maybe if you hold the question.
Oh, okay, yeah, sure. Yeah.
Okay. So very good. So indeed, as the question was asked, we can compute now immediately the 2-point function of these modes. And we will find that the 2-point function of these modes. Now, this 2-point function of these a omega L's, as I said, were basically near horizon modes, right? So remember, by the way, there's an L which I'm kind of, I've always set it to be the same, because if you put an L prime here, you just get delta LL prime. Okay? So I'm just setting this to be the same. So this, in fact, is 1 by 1 minus e to the minus 2 pi omega naught. Provided, this omega is related correctly to this omega naught. Okay? But as people were asking, omega naught is just omega by k. Okay? So provided you define beta as 2 pi by k, you will find that a omega L into a dagger omega L is 1 by 1 minus e to the minus beta omega. Okay? And that's actually the result we wanted to get. So you see, we've got the correct temperature, which is 2 pi over the surface gravity. And that automatically tells you that if you look at, remember, these a omega L's are slightly smeared versions of the global modes. And this is automatically telling you that if you look at global modes, so the way you should think of a omega L is as a global mode with the frequency omega and L, but it's not delta function normalized. It has some slight smearing. And what the last formula, the box formula at the bottom, is telling you is that if you look at such a global mode, which has frequency omega and L, then this global mode is occupied exactly the way you would expect a thermally occupied mode to be. And you see, this just drops out of the fact that the near horizon modes, when defined with the frequency omega naught, have an occupancy which is 1 by 1 minus e to the minus 2 pi omega naught. Then there is a relationship that we computed between this omega naught and omega. And then we define this beta. This is just a definition of beta for us. Oops. This is the definition of beta. And with this definition of beta, you see that the modes are thermally occupied. Of course, this beta is the inverse temperature. It is the inverse temperature because from the fact that you have these modes which are thermally occupied, you can interpret beta as the inverse temperature of the black hole. But you see that just from putting together the results that we had for near horizon modes and the near horizon expansion of the fields, we find that the global modes with frequency omega and L, provided you smear them a little bit, have an occupancy which is exactly what you expect a thermal occupancy to be. Okay.
Suvrat, there's a question in the chat
Go on, please.
asking why is the final result L independent?
It is L independent because for a Schwarzschild black hole, it is indeed the case that the final result doesn't, the occupancy of the modes depends only on omega and doesn't depend on L. If you took a Kerr black hole, then this would not be the case. But this is a physical fact which comes out of our derivation, but it's true you can derive in other ways as well. That the final occupancy does not depend on L.
I have a question. Okay, go on.
Yes, sir. Yeah, no, Tunir, you can go on. There's a raised hand.
Okay. Shouldn't the occupancy be A dagger A instead of A dagger?
There is another occupancy for A dagger A. This is the occupancy for A dagger. The A dagger A occupancy has an e to the minus beta omega in the numerator. You can always get that occupancy by using the fact that A dagger commutator is 1. This is the answer for A dagger. If you put the A dagger first, you'd get an additional e to the minus beta omega in the numerator.
Right. Okay.
There's a raised hand, maybe.
Yes. So my question is about the number. It's about the modes that are going to plus infinity. These are already global modes that can be observed by a very far away observer.
Yes. They are already global modes.
Yeah, okay. Thanks.
I'm going to say a little bit more about that. Please, do you have a question about that? I'm going to talk about that in a minute.
Yeah, please continue.
Okay, fine. Okay. So let me say, the same way we can actually also derive something.
I have a question.
Your question? Someone has a question? Yeah.
Hi.
Yeah, go on. Yeah.
Hi. So the near horizon modes had this 2-point function independent of the state, right? When we derived it. It was
independent of K. Yeah, the near horizon modes were just defined with some U. Yeah, correct. Yes.
No, independent of the state, I meant.
Independent of the state, yes.
But then the 2-point functions of the global modes depend on the state, right? By the choice of global modes.
Yeah. So let me say a little bit more. Yeah, indeed, they do depend on the state, right? So how did it happen?
But when did we make that choice? And it seems as if for any state I should have a thermal.
It is true, right? And indeed that's the correct answer. So let me say a little bit more. Okay? Just wait for a minute. Maybe I'll answer the last 2 questions.
I mean, there should be some state where you don't see the thermal spectrum, right?
Yeah. Thank you. I'll answer the question. Give me a minute. Okay. Let me just say a little bit about the Atilla modes. Okay, we are going to come back and talk about the Atilla modes. But let me remind you that we could, if you look at the Atilla modes. There's an Atilla NH mode that we define, okay? And this Atilla NH mode will become Atilla into omega naught KL, where this Atilla omega L is a smeared version of A tilde omega L, okay? So there are some other global modes that we defined behind the horizon. And if you look at these tilde modes, then it will so happen that this A tilde omega L will be a smeared version of these A tilde omega L modes in exactly the same way. We are going to actually set that aside for now because if you're just talking about the exterior of the black hole, we don't need this, but we're going to come back. This is actually going to be an important part of our story, but we will come back to it in later lectures. But let me just mention it now. Okay, let me go back to these A omega L modes, which were the modes outside the horizon, and indeed ask, what is it that we put in to get the answer? Okay? So the first thing, to get the thermal occupancy, for these A omega L modes, what were the assumptions we made? We made only 2 assumptions. We assumed that the horizon was smooth, and there was a late time emergent T goes to T plus delta T isometry. Okay. This was, the second part was very important to be able to link the near horizon modes to the global modes. Okay. If the second part had not been there, if we had not had the isometry, you can check that we would not have been able to link the global modes to the near horizon modes. Okay. The first part is very important for the question that I think Akhil just asked, which is that, it is the first part that told us that, so this is what fixes the occupancy of the near horizon modes. Okay. This is what allows us to relate the near horizon modes to the global modes. Okay. So the only states where the result that we derived is not true are the states where the horizon is not smooth. So if you look at a state where the horizon is smooth, that forces, and there is also this late time emergent T goes to delta T isometry, which we expect for a black hole. So if you form a black hole, you expect from the classical geometry that both these things are true, and that forces you to the fact that the global modes are thermally occupied. Okay. So it might seem a little quick, this derivation we have, but I think it's actually a nice derivation, and it kind of makes clear the short distance. Remember in the first lecture, which was maybe a long time back now, I emphasized that the physics of Hawking radiation relied on a combination of some short distance properties and some long distance properties, right? The short distance property we derived by looking at the near horizon modes, and the short distance property we used here was the fact that the horizon was smooth. And that's what fixed a certain occupancy for the near horizon modes. The long distance global property we used was, the fact that you have this isometry, and that forces the near horizon modes to be global modes. Okay? So we find that, once we've done all this work in defining these near horizon modes and working out the near horizon expansion of the fields and all of this stuff, we find that the result for Hawking radiation just indeed drops out. And precisely as was asked, it is indeed the case. Remember that this A omega L is proportional to A omega L. Okay? And remember that A omega L is outgoing. So let's say we take a massless field, so we can talk about what happens at scribe plus, is outgoing at scribe plus. Okay. In fact, we had some expression for scribe plus. A omega L didn't exactly behave like e to the I omega r star at scribe plus, but there was some expression we put in which is called T omega L, and that T omega L is what's called a gray body factor. Okay? It's the fact that even though these modes A omega L's or slightly smeared versions of them are thermally occupied, if you compute the stress tensor far away, it is not, if you have some observer who was far away and you try to compute what the stress tensor was or what the natural modes for you were, those modes may not necessarily be these A omega L modes. So the stress tensor far away also depends on the properties of this function f out. Okay? Of f out. And indeed, if you look at the behavior of f out as r goes to infinity, that gives you what is sometimes called the gray body factor of the black hole. Okay, but those gray body factors are a complication. I mean, they're not a complication. They're what we would really observe if at some point we were to observe a black hole far away. But for the question that we want to ask, which is the question of what is thermally occupied, these gray body factors are kind of just some messy factors that come from solving the wave equation, starting with e to the I omega r star and going out to infinity and seeing what the wave equation, what the mode that you're looking at becomes there. It's some completely straightforward computation, but it kind of messes up the beautiful result we have. Okay? The beautiful result we have, which is the result we want to focus on, is that these A omega L modes, which were defined as modes which were outgoing near the horizon and had some normalization near the horizon, are thermally occupied. Okay. So these gray body factors are important if you really wanted to observe a black hole, but it is indeed the case that if you work in terms of these A omega L modes, they're just exactly thermally occupied. They don't have any gray body factors sitting in front of them. Okay, so that's an important thing, and so maybe as I said, we'll have a question in the assignment about these gray body factors. Okay. Let me also say one more thing, which some of you might have noticed, which is that our derivation does not constrain B omega L. Okay. It does not constrain b omega L because b omega L didn't appear in these near horizon modes. It was the term that was multiplying v to the I omega by k and v to the minus I omega by k. Right? So b omega L is just basically totally unconstrained by demanding that the horizon be smooth and by demanding that you have this late time isometry. In fact, there are several choices you can make for b omega L. One choice is that you put b omega L in the vacuum. This choice is what is sometimes called an Unruh state. Another choice is that you put b omega L, you populate b omega L thermally, which you could do. Right? So you populate b omega L thermally. This is what's sometimes called a Kruskal state. Okay? And by doing this, you can actually change the flux that comes out at infinity, right? Populating b omega L thermally is like taking a black hole and feeding it all the time with some flux that's coming in from infinity, and you could choose to do that, right? Or you could choose to just say we are not feeding it from stuff that's coming far away and these b omega L's in the vacuum, and you can make other choices as well. Okay? You could choose something in the middle, but the point is that what Hawking's derivation constrains are these outgoing modes near the horizon, and it's these outgoing modes near the horizon that have to be thermally occupied. There are in addition these ingoing modes about which Hawking's derivation doesn't say anything, and you could populate them as you like. Okay? So I emphasize that we have arrived, I think, at a very robust, a very beautiful result, and this very beautiful result about these modes near horizon, outgoing modes being thermally occupied relies on a combination of short distance physics and some long distance physics. The short distance physics being the presence of a smooth horizon and the long distance physics being this late time isometry. Okay, so I'm going to stop here for questions, and then I'll go on and talk about ADS after this, because the ADS story is almost entirely parallel, but I'll just yeah. I see there's a question here which says, where did we use the isometry? We use the isometry in the fact that that's what allowed us to expand these global modes with factors of e to the minus I omega t. And that is the reason the global modes started behaving like u to the I omega by k near the horizon. Okay? If we hadn't had this isometry, then we would not have had the global modes behave in this way near the horizon. So that's why we use the isometry. And that's the relation, that's the reason these global modes got related in a specific way to these near horizon modes. Okay, are there any other questions about this?
Yeah, actually, there's a raised hand. Maybe Ash,
please,
if you can.
Hello.
Hello, is there some audio problem maybe? Or?
Yeah, I think his audio was not working.
Okay, maybe we can come back to it later.
Yeah, sure.
Okay. Fine. Okay. Okay, so let's move on to a next step, which is Hawking radiation for ADS, black holes. This is actually a simple exercise because almost everything is going to be parallel. Okay, so we're just going to have to do the same things again, and almost everything will be parallel.
Sorry, before you maybe start, there's one more question in the chat.
Yeah.
What are the advantages of this derivation with respect to the naive Rindler analogy?
Thank you. So so Hawking's derivation is not the naive Rindler analogy. Hawking's derivation is by doing ray tracing. Okay? If you do ray tracing, it's hard to understand how you should correct things. In this derivation that we have, I said there were these ... terms. Maybe the isometry at late times is not exact. Maybe there are interactions you need to be careful of. But you could, in principle, have worked out everything carefully, right? You could have taken this derivation and you could have worked out carefully what these 2-point functions have to be, and you would have got some constraints on how these a omega L modes have to be occupied, and you would have found that there are subleading terms which are not constrained. Right? So you could have, in principle, you can in principle work out this thing more precisely, and it's slightly more precise, I think, than the geometric optics derivation. Although the geometric optics derivation, as I said, has the advantage of giving us some insight. As opposed to the naive Rindler analogy, I mean, I think this is well, okay. I always, as I said in the Rindler case, I always would get confused saying, we are saying that locally the horizon looks like a Rindler horizon, but what does that really mean? And how much does the fact that we are not globally in Minkowski space matter? Why is it that we are allowed to say stuff like the horizon looks locally like a Rindler horizon, even though globally the state is something different? So where precisely do we use the global properties of the state? And I think this makes it clear where we use the short distance physics and where we use the long distance physics. And I think that's one of the advantages of this derivation. I have to say another advantage of this derivation is it's given us some technical tools that we'll keep using as we go throughout this course. But I also feel it makes these conceptual questions clear about where short distance and long distance is important. And it also, in principle, allows itself to be corrected to subleading orders.
Okay, and yeah, I think Ashif, whose audio went bad, he wrote the question in chat. He's asking, what's the definition of vacuum here? The Unruh vacuum will not be a vacuum for Kruskal observer.
Yeah, I don't know what you mean by vacuum here. I actually didn't use the word Unruh vacuum, even though if you look at Candela's paper, some in older papers they use the word vacuum. I don't know if I used the word vacuum. I didn't please write the word vacuum. I just said Unruh state and Kruskal state. So there are two possible states which are just controlled by what you did with B omega L. When I said B omega L in vacuum, that just means that you choose B omega L on the state to be 0. So B dagger omega L doesn't annihilate the state, but B omega L annihilates the state. This is what it means for B omega L to be in the vacuum. But yeah, you could populate B omega L thermally, which means you could take slightly smeared versions of B omega L and you could make them have the 2-point function, which is a thermal 2-point function. That's what it means to populate them thermally.
Okay. There's another question by MO who's asking, how about the Transplantation problem of Hawking?
Yeah. Thank you. You see we don't have a Transplantation problem here. We did use short distance physics. We used short distance physics in demanding that the near horizon modes be correctly entangled, but we didn't use Planck scale physics, right? And the reason for that is, we didn't have to trace things back all the way to scry minus. We just said, we are demanding some short distance behavior at the future horizon. We are demanding that the short distance physics be correct, and that is already enough to relate what happens at scry plus to what's happening at the future horizon. We didn't demand, we didn't try and trace things back all the way to scry minus, and that is important, and that's the reason there is no Transplantation issue in this. It's clear we never needed Planck scale physics or beyond Planck scale physics. Yeah. Okay. So I hope that's good.
It. Yeah, you can go.
Thank you. Okay, great, fine. So let's now talk about Hawking radiation ADS, and as I said, we can do this fast, and that's because everything is going to be parallel. So we are always actually in this course going to talk about things which are asymptotically global ADS, okay? And global ADS, so asymptotically. And that means that as r tends to infinity, the metric tends to this, which I'm sure many of you are familiar with, but just to remind you, and we always in ADS D plus 1. The reason to be in global ADS is just that it gives us a nice infrared cutoff. So then we don't have to worry about, we could do everything we are doing in Poincare ADS, but global ADS gives us infrared cutoff. It gives us finite entropy, so we don't have to worry about regulating entropies and so on. In some sense, in flat space, we do have to worry about all of these issues, and at some point we will talk about these issues. But we'd like a change in ADS, so we'd like one setup where we can talk about a system which does not have IR complications, which is global ADS, and then we have flat space, which does have IR issues, which will be important for us. But whenever we talk about ADS, I just want to say in this lecture and later, unless I say so explicitly, we are always going to talk about asymptotically global ADS spacetimes. The ADS radius is always going to be set to 1. So maybe we'll display it once in a while, but in general, the ADS radius is 1. So now we want to consider black holes which are formed from the collapse of matter. So we want black holes that at late times, once again. Okay. So now the ADS scale actually gives us a natural notion of of units of time. So here we can talk about t being much larger than 1, by which we mean t being much larger in the ADS scale. So we have some black hole which is formed from collapse. So we have some black hole formed from collapse. We wait like many times the ADS time. And we are interested in geometries that become spherically symmetric at late times. You could, of course, consider other kinds of geometries, but that's not going to be important because everything interesting that we want to say is already visible in spherically symmetric geometries. And it turns out that the metric is going to be, in fact, this is the same equation literally as the equation I wrote earlier. The metric at late times tends to this. Okay? But f of r has a slightly different form. F of r looks like 1 plus r squared minus mu by r to the d minus 2. So in flat space, it was just 1 minus mu by r to the d minus 2. But here it's 1 plus r squared minus mu to the r to the d minus 2. And the relationship between mu and mass have the same relationship as in flat space. Okay. So this mu is like a mass parameter. It's what sometimes is called a mass parameter. It's not literally the mass, but there's some dimension dependent constant that one can work out that relates it to the mass. I already wrote that constant in the last lecture, and so I won't write it again. Okay. The horizon is once again at f of RH equal to 0 is the root of f of RH. This root, so this is now some complicated equation. One needs to solve the horizon in flat space was just at mu to the 1 by d minus 2. Here you have to solve this f of RH equal to 0, but there's some solution. And let me just draw the Penrose diagram just so we are clear. Maybe I can also answer a question that we had yesterday. So ADS, global ADS looks like a cylinder. This is one way to think of global ADS, okay? Which is just a cylinder, but the cylinder, the presence of a black hole develops some singularity here. And then there's a horizon. This is the horizon. Okay. And this horizon was formed at some point by, by the collapse of some matter. Sorry. So can we mute everyone?
Yeah. Maybe.
Yeah, fine. Okay, thank you. Yeah. Okay. So this horizon was formed maybe by the collapse of some matter, and the matter maybe came from the boundary, or maybe it already existed in the state. It doesn't matter, right? We don't care where this horizon, what the infalling matter is. So I'll just shade this infalling matter. So there's some infalling matter. This is the singularity. This is the horizon. And we are once again interested in some region which is here. Okay. Yesterday, actually, there was a question about how one defines. It's again come next to the horizon. Let me just. There was some question, I think, which Prahar asked about how this region is defined. And I think I wasn't very clear. So indeed, maybe one good way to, so I said yesterday that the region is defined by looking at times which are large but not very large. And indeed, perhaps a good way to do the definition instead is to go to some globally well-defined coordinates like the UV coordinates. And then this region is a good notion, is a good, region in the UV coordinates, which is near u equal to 0, which is where the horizon is, and for some range of v's. Indeed, this corresponds to if you go far away, if you go a little bit away from u equal to 0, this does correspond to saying that you don't want times to be too large. But I do want to emphasize that this region of interest includes the horizon and the region beyond the horizon and doesn't get cut off at some point before the horizon. Okay. So once again, just to say the same thing. So we are interested in times in a, let's say we're interested in a late infalling observer. Okay. So late infalling observer needs to understand the physics of this region. And so late infalling observer might have some trajectory that looks like this. The late infalling observer starts from here. So I now have lots of white lines, but here's my infalling observer. Late infalling observer starts from here, and then the observer intersects this region of interest and then goes and ends the person's life at the singularity. but we are only interested in what happens to the observer while the observer is outside and just a little bit inside the horizon. But as I said, this late infalling observer is late enough that the infalling matter, the perturbations have died out, or effects of infalling, better to say effects of infalling matter have died out. But we don't want to consider times which might be extremely long. In extremely long times, it might be that there's Poincaré recurrence or something else happens. So we don't want to consider times which are extremely long, but we do want to be at times which are much larger than ADS time, so that the effects of the infalling matter have died out and the geometry has settled down to the ADS Schwarzschild geometry that we wrote previously. Okay, good. So this is almost the same setup that we had in flat space, except the Penrose diagram looks slightly different. So you should be comfortable with this Penrose diagram as well. Okay.
So there was a question. Sorry, there was a question in the chat related to what happens when t is of order 1.
Yeah, something complicated happens when t is of order 1, right? If you're close to the infalling matter, the metric has some perturbations which have to do with the details of the infalling matter, and you could do that. You could take some specific kind of infalling matter and do some Oppenheimer-Schneider kind of collapse, then you would find some metric. By the way, when I say t is of order 1, I mean that I said t equal to 0 at the point when the infalling matter started falling in. And okay, there's something complicated that happens near t equal to 1, but we don't want to bother about that. We want to go to late times where all the effects of the infalling matter have died out. And it's an interesting fact. It's a fact that in fact underlies the first paradox we're going to find in the next lecture, which is that the geometry doesn't care about all these effects once you go to slightly large times. So all of these effects of the infalling matter cease to matter at late times. The black hole settles down to an ADS Schwarzschild geometry, and that's when we want to consider the black hole.
Okay, there's actually a raised hand now. You want to take it now, or?
Sure. Yeah.
Okay, maybe Osama, you can go on.
Yes, thanks. So there's a question I wanted to ask about the global modes when we write the expectation value of A plus of omega is thermal, and that's at I plus. So I'm wondering here.
These modes were just modes which were, these modes are just some modes which are multiplying certain modes. So, at I plus, there are some gray body factors that will be important if you compute the stress tensor, which I think I wrote somewhere. Yeah. So stress tensor far away depends. Yeah.
But I don't think that affects my question, which is about causality. So it seems like these are instantly transformed to a very far away observer from the black hole. So a very far away observer can observe these modes if a black hole just happens to form very far away.
No, I don't think that's true. If you look at the Penrose diagram, this radiation is observed. I know where we drew the Penrose diagram, maybe somewhere many slides before. Yeah, remember, that's why we have this late time isometry, right? So the observer who observes these modes is like somewhere here. So you have some observer who's at late times, and that's when this isometry becomes important. That's why this isometry is important. So the black hole geometry has settled down. Once it settles down, there are some modes outside which settle down into a thermal state. Right? So when the black hole initially forms, and maybe this is related to the earlier question about what happens near t equal to 1, there are some quantum effects that start occurring the moment the horizon forms, right? There are some quantum effects, but the form of those quantum effects at initial times when all the effects of the infalling matter are there is complicated. But when we look at late times, these quantum effects become simple, and the observer who observes these modes is sitting here. And there's no loss of causality because, in fact, there's some, as I said, there's some isometry in T. So, what we are exploiting is the fact that the geometry has settled down and the quantum state has settled down as well. And we're using the fact that the quantum state has settled down to derive what the form at I plus has to be by relating it to some near horizon mode. So that was the point of the isometry. Does that answer the question?
Yes, it does. But there's a little follow-up question that's very general, but very simple. So if you look at a commutation of phi x1, phi x2, of, let's say, a scalar field. And if x1 and x2 are space-like separated, then this commutation, the expectation value of it would be 0. But I'm wondering if there is a horizon between x1, x2, would it still be 0?
Yeah, absolutely. The fact that there's a horizon doesn't change the local properties of these commutation relations. So, in fact, we already used when we defined these A's and Atilla modes. The reason the A's and Atilla modes commute is because of what you said, because when x1, x2 are space-like separated, they commute. And locally, all that matters is that they should be space-like separated. And they don't actually exactly commute. There are effects that come about because of gravitational effects, but within quantum field theory, local quantum field theory in a curved spacetime, it's exactly true that operators at space-like separation commute, and that doesn't care about whether there's some horizon or not. It's just true. It just depends on whether the points are space-like or
not. Because the interpretation that I always understood is that because there are modes that are traveling from x1 to x2, and also modes that are traveling from x2 to x1, and these cancel each other out. But I'm thinking if there's a horizon in between, then one way doesn't work. Of going one
I'm not sure. I don't think that's the right way to understand the fact this microcausality. In fact, microcausality is a statement that there is no information that can travel from one to the other. So, if you make an excitation at x1, it doesn't actually get to travel to x2, and the same way, vice versa. So it's the fact that if you make an excitation at one point, you can't detect it at a space-like separated region. It's not that there are modes which travel, and cancel things out. So it's just the fact that it's a more basic property, and it's not because things are traveling between one to the other. It's just that information you can't make an effect somewhere else by turning on a source right now here.
Okay, thank you very much.
Yeah, thanks. Yeah, okay. So let me go back to my ADS derivation. Thank you. So we want to look, let me just say one more thing about conventions. So we are interested in fields. So we consider fields which are normalizable, which are normalizable. Okay. And that means that phi goes to 0 as r tends to infinity. Now, the physical interpretation of considering, actually this is not only true for fields, but for all other dynamical operators and not only scalar fields, but the metric as well. The physical interpretation of this is that we are considering a system undisturbed by external sources. Okay. So sometimes when we do ADS CFT, it's convenient to think of a system which is disturbed by external sources and ask, how did the system respond to an external source? But we want to consider physics which is just autonomous. So we have an ADS system, and we are going to consider physics which is just autonomous. So it evolves autonomously. And the fact that the physics evolves autonomously, you have some scalar field in ADS, it dies off near the boundary. So you're not throwing in stuff from the boundary. This scalar field is just sloshing about in ADS, and it evolves the way it does. And so this is a convention that we'll adopt all the time. Okay? It actually turns out that even though I impose the boundary condition that phi goes to 0 as r tends to infinity, for fields of mass m, something else happens. It in fact turns out that phi goes like 1 by r to the delta. So it dies off, not just goes to 0, but dies off as a particular part of r at large r, where this delta is related to the dimension and the mass of the field in the following way. Okay, and this delta is also the operator dimension. If this phi is also the dimension of the dual operator to phi. Okay, so if you have some weakly interacting scalar field in the bulk, there's a dual generalized free field primary operator that's dual to it, and the dimension of this operator is delta. But I just say that for general information. We are not going to need this, but we will make reference to this fact. Even though we impose only that phi goes to 0, phi in fact goes to 1 by r to the delta at large r. Okay. Now, as usual, we'll introduce tortoise coordinates.
Suvrat, do you mean delta? You said d over 2 plus minus, or was it just plus? Which sign?
Indeed. Sorry, we'll always take the plus sign. Thank you very much for the correction. Thank you. I'm used to writing plus minus because there are indeed two routes for delta for the faraway behavior of the field. But in fact, if I took the negative route, I would not find this normalizable solution. Thank you for the correction. Indeed, I always want to take the positive route. Thank you. Okay. So in these, so we'll introduce tortoise coordinates. And these tortoise coordinates are once again just introduced as dr star as being dr by f of r. Okay. Now near the horizon, once again, r star goes to minus infinity. This is the same as what we saw in flat space, right? Things are almost exactly the same as what we saw in flat space for the tortoise coordinate near the horizon. But near infinity, r star goes to a constant. The reason is that f of r doesn't go to 1 as r tends to infinity, okay, but f of r goes to 1 over 1 plus r squared as r tends to infinity, and that has a finite integral, and so r star goes to constant. The precise constant that r star goes to is something you can fix. You can set the origin of r star. It might be convenient to choose that constant to be 0. It might be convenient, in fact, to choose it to be something else. But the point is that r star doesn't go to infinity. Near the boundary, it kind of goes to a constant. Okay. Then if we expand the field, the same field phi, with this boundary condition that it has to go to 0 at infinity, we will once again be able to write down an expansion. And that expansion, let me now just write down, looks like this: a sum over L, a sum over angular momenta. And I'll just explain what this is, what the notation is. Okay, where this solution is now a standing wave solution to the wave equation. Why is it a standing wave solution? Because, we are not allowing the field, we have imposed a boundary condition for the field at r equal to infinity. So we have held the field fixed at r equal to infinity. And that's why, we are not allowed to freely modify the e to the I omega r star and the e to the minus I omega r star terms the way we were allowed to do in flat space. So this is one difference between the way we are treating ADS and the way we are treating flat space, in that in ADS, by imposing normalizable conditions, we have forced, we have killed one solution of the wave equation, and we have only these standing wave solutions. Okay. And these standing wave solutions have the form, we will demand that the standing wave solution goes like e to the I omega r star plus some e to the minus I delta, a phase that depends on omega and L, into e to the minus I omega r star. Okay. How am I doing on time? Okay. Maybe I can justify quickly why this has to be a phase. This phase, in fact, is like these d omega L's and h omega L's, except that now we don't have a choice of g omega L and h omega L. And this phase, in fact, also has interesting physics. This phase has to do, you can relate to the quasi-normal modes of these ADS black holes. But let me just try and explain right now why this relative coefficient has to be a phase. Okay. You see, the point is that the field has to obey canonical commutation relations. So the canonical commutation relations are that phi and phi dot look like delta in the tortoise coordinates, okay, into some sphere delta function. So the canonical commutation relations, once you put in the factors, look like this. Okay. But now think of putting in this expansion that you have here and trying to satisfy the canonical commutation relations near the horizon. Okay. So this is the expansion for the field. The field must obey the canonical commutation relations everywhere. Let me in particular try and demand that the field obey the canonical commutation relations near the horizon. Okay. If you do that, okay, what will you find? Okay, so there are various factors of R and so on, but the important thing that you will find is that we will, so let me put, right, you can work out all the factors, but you will find something that looks like d omega, okay, into a omega L into a dagger omega L, okay, and something which has an e to the I omega r star minus, let me put an omega prime, minus an omega r star prime. Okay. And let's say you had some term here which looked like, let's say this term here was not a phase but looked like g omega l. Okay? So let's call this g omega l for a minute. Then what you would get here in addition to this term is a term that looked like plus g omega l into g omega prime l prime star into e to the minus I omega r star plus omega prime r star prime. Okay, so I haven't done anything here. I just took the field, I commuted it with its canonical conjugate. When I do that, I have some commutation relations between the a omega operators and their canonical conjugates, which is a omega. I've set the angular momentum to be the same because that's, we assume that has a delta LL prime. So there's an a omega and an a dagger omega prime. And then with that, there are various other factors of omega and so on. And that's why I put a tilde here. And I am not writing down those factors of omega. And then you get some term which looks like e to the I omega r star minus omega prime r star prime. And then you have this g omega l factor, which is the relative phase between the e to the I omega r star and the e to the minus I omega r star term. So you have this g omega l factor, and then you have this g star omega prime l prime factor. And then you have some additional terms, okay, which are linear in g omega l. Okay. But these terms multiply something that looks like e to the I omega r star plus omega prime r star prime. Okay. Do you see this form? You have some expression which looks like e to the I omega r star plus g omega l into e to the minus I omega r star. You multiply two of those terms together, you'll get four terms. Of those four terms, here's one, here's the second, and then there are two more terms which have terms which are linear in g omega l, which multiply something like this. But remember, in the end, you want to get a delta of r star minus r star prime. How could you get a delta of r star minus r star prime? You could only get it if this commutator was proportional to a delta of omega minus omega prime. Okay, but remember that the integral over omega is an integral over positive omega. So this expression is still only going to give you an e to the I omega into r star minus r star prime. The only way you can get the other term, which is an e to the minus I omega into r star minus r star prime, is if this is 1. Okay. Okay. And that's why, just satisfying the canonical commutation relations near the horizon forces you to have this expansion. Okay, forces this to be a pure phase. Okay, if you didn't follow that, it's not so important. You can take it, you can work it out yourself. But it's important, the result that you need to remember is just that if you look at the expansion of the field near the horizon, the expansion of the field near the horizon has this term which looks like e to the I omega r star, which I chose to normalize with a factor of 1. It has another term which looks like e to the minus I omega r star, which comes now with an e to the minus I delta omega l. And the reason these terms have to come together, I'm not allowed to have independent coefficients for this one and this one, is because I impose normalizable boundary conditions at infinity, which allowed me to have only standing wave solutions. Okay. Okay. The same way behind the horizon, we can write down an expansion of the field, which now looks like some a omega l into e to the minus I delta omega l e to the minus I omega t y l omega. Let me just write down the expansion and I'll explain it in a second. Plus the Hermitian conjugate, where this f tilde is a solution of the wave equation that has the property that as r goes to rh minus, it goes like e to the minus I omega r star. Okay. Now, this is exactly like what we did in flat space. There also we had an a tilde. Okay. We had an a tilde and we had a C operator. That C operator was linked to the A and B operators outside by continuity. Here it's very simple. I don't need to introduce a C operator. I just use continuity to, to determine that the C operator had to be A omega L into e to the minus I delta omega L. So this just came from continuity. And then once again, we find there are new modes. These are new modes which appear behind the horizon, which are not related to modes outside the horizon in any simple way. And later in the course, we will discuss these modes some more. Okay, so this is exactly parallel with what we did in flat space. We've written down an expansion outside the horizon, and we've written down an expansion inside the horizon. Okay, okay. So now we are almost done. The last thing we need to do is now define the near horizon modes in ADS, and we will get back the expression that we got for the occupancy of these A omega modes. So let me just do that. Okay.
Suvrat, there's a raised hand. You want to take it now?
Can I just complete what I want to say, and then maybe
sure,
we can go on? I just want to go on for a few minutes.
Fine.
And
sure.
I'll take questions at the end. Okay. So as usual, as in flat space, okay, we introduce near horizon modes. Near horizon modes. Okay. And once again, we'll find exactly the same result for these near horizon modes, which is that if these near horizon modes become some A omega naught K into L, become some A tilde omega naught K into L, where this K is once again, F prime RH by 2. It's the same quantity that appeared in flat space. And this A omega L is a smeared version of these A omega L modes. Okay. And this A tilde omega L is a smeared version of the A tilde modes. Okay. And once again, we find that these smearing functions, you can work them out explicitly. They're different in ADS than they are in flat space. There's some smearing functions you could work out explicitly, but these are sharply peaked about omega equal to omega prime. Okay. And we don't need to work these smearing functions out explicitly, because we know from the definition of the near horizon modes that these modes are normalized in some nice way so that these commutators are 1. And we find that there's a thermal occupancy of these modes. The thermal occupancy of these modes is just that A omega L into A dagger omega L looks like 1 by 1 minus e to the minus beta omega. Okay. So this is the same result we had in flat space, now written in ADS. Okay. There is a difference though between the situation in flat space and the situation in ADS. And the important difference is that in ADS, we don't have any flux at infinity. Okay. The reason we don't have any flux at infinity is because in ADS, we've imposed these normalizable boundary conditions. So even though A omega L or A omega L smeared is thermally occupied, there is no flux at infinity. Okay, so this is a difference in the physics between ADS and in flat space, which has to do with the normalizable boundary conditions we've imposed. And so we do find that there is this Hawking radiation, but the Hawking radiation is not interpreted in terms of a flux at infinity, but rather we obtain a black hole with a thermal atmosphere around it. Okay, and once again, the fact that this A omega L is thermally occupied can be turned into some statement about the 2-point function of operators near the boundary. This 2-point function, just as it did in flat space, involves some gray body factors. So, the gray body factors come from the fact that the standing wave solution as r goes to infinity has some factors which look like g omega L by r to the delta. It had to go like r to the delta, but there's some leading constant that appears there. And that tells us that if you look at the dual modes of the operator O omega L, the dual operator, that looks like square root of G omega L into A omega L. Okay. So I emphasize that it's not that the operator 2-point functions are given by this if you smear them correctly. The operator 2-point functions have this additional factor of G omega L, which in fact has to do with the commutators that these omega L's have with O dagger omega L's, which are different from the commutators that A omega L's have with A dagger omega L's. And these you can, these square root of G omega L's, you can interpret as the gray body factors. And they once again have to do with the fact that even though these A omega L's are thermally occupied, if you try and interpret what's happening on the boundary in terms of operators which are normalized in some other way, there is some relation between these two which comes by solving the wave equation. But this relation, the last two lines on this board are not important. What is important is the first part, which is that in ADS as well, just defining the near horizon modes and going through the same procedure, which I did fast because it's exactly identical to what happens in flat space. We find that you get a black hole. The black hole now doesn't have flux at infinity, but develops a thermal atmosphere. Okay, so let me just summarize, and then I can stop and we can have some discussion. So in these two lectures, we have, we did a lot of work before these two lectures, in the first three lectures, in defining these near horizon modes and in working out the expansion of the field near the horizon. But we see that once we have all of this in hand, if you just put together the near horizon expansion of the field, the fact that there is this isometry which develops in both ADS and in flat space, and you put this together with this analysis of these near horizon modes that we did previously, you find immediately the result that we see on this slide and the result that we had some slides earlier in flat space, which tells us that a black hole develops a thermal atmosphere. The thermal atmosphere leaks away out to infinity in flat space, and in ADS, it just sits around and sloshes around because of the normalizable boundary conditions we imposed. So we have now derived in a rather robust way the phenomena of Hawking radiation, and in the next two lectures, we'll then go on to discuss the first paradoxes, which are first Hawking's original paradox and its potential resolutions. But this physics, the physics of Hawking radiation, is very fundamental to the entire discussion, and we'll keep referring back to these issues again and again. Okay, so thank you very much for listening. I'll stop here for questions. We're also out of time, so I realize some people may have to go, but the others who would like to stay around, I'll take questions now. So thank you.